Hello, this is Dr. Hanaa Assil, and this is about transition metals and their chemistry. So this is mainly for the A2 chemistry at Edexcel. Let's talk about the chemistry of transition metal. Transition metal is defined as a D block element, so something in the D block, which is in the middle, that forms one or more stable ions with incomplete d orbital. So this is the definition of a transition element. It must be in the d block and it forms one or more stable ions with incomplete d orbitals. So if we look at the electron configuration of these elements, remember that when we're filling the energy levels, we fill the 4s before the 3d. So for example, if I'm writing electron configuration of vanadium, vanadium has 23 electrons. So we're going to distribute the electrons 1s2 to s2 to p6. Then 3s2, 3p6, and then I put into the 4s first before the 3d. And when we're filling these orbitals, we put the 2 electrons into the 4s. I'm left with 3 electrons to put into the 3d. You remember that the 3d sublevel has 5 orbitals. We put 1 electron into each orbital first before we do any pairing. So when we form ions, remember that we remove electrons from the 4s first. So while filling the electron configuration, we fill 4s before 3d. But when we're trying to form ions, we need to remove electrons. We remove from the 4s first. Remember, the 4s is in the 4th energy level. So the electrons in the 4s are lost first, and then we remove electrons from the 3d in order to form the ions. Now, exceptions to what we just said. Remember, if I have chromium, chromium has 24 electrons. How am I going to distribute it? We distribute it 1s2 to s2 to p6. 3s2, 3p6, then I'm supposed to put 4s2, and then I'm left with 4 electrons, so 3d4. But this is not what we actually do, because we need to make the sublevels half filled. If they're half filled, they're more stable. So instead of writing it 4s2, 3d4, we write it 4s1, 3d5. That means the 4s and the 3d are now half filled. So this is more stable. The other exception, of course, is copper. Copper has 29 electrons. So when I distribute them, 1s2 to s2 to p6, 3s2, 3p6, I'm supposed to put 4s2, 3d9. But that's not what we do. Because in that case, the 3d just needs one more electron to be completely filled. So I remove 1 from the 4s, put it into the 3d. So what we actually do is 4s1, 3d10. In that case, the 4s is half filled and the 3d is completely filled. So this is more stable. Okay, what are the ions that we can form? Remember, transition metals, one of their characteristics is they have variable oxidation states, or different valencies, or different forms of ions. This is because I can remove electrons from the 4s and from the 3d. So for example, if I have vanadium, we said this is the distribution for vanadium, 4s2, 3d3. Now, when vanadium wants to make an ion, the most common oxidation state for any of these metals is +2, because I will remove the 2 electrons of the 4s. So the first kind of oxidation state is +2, in which we have removed the 2 electrons from the 4s. Now I'm left, for example, with vanadium with 3 electrons in the 3d. I can remove them one by one. so that the maximum is when I have lost all the electrons and in the 4s and in the 3d. So I can have vanadium plus 3, vanadium plus 4, and vanadium plus 5. So that is the maximum that I can have. So remember that the lowest is usually the one where we take the 2 electrons from the 4s. So the lowest oxidation state for most of these elements is +2, and then we remove 1 each from the 3d until we have removed all of them. So the maximum for vanadium is when I have removed 2 from the 4s and the 3 from the 3d. So the maximum oxidation state is +5. So for each of these elements, you can determine these would be the most common oxidation states. Titanium is 4s2,3d1. So the lowest or the most common oxidation state is when I have removed the electron, the 3d, and the electrons in the 4s. So the lowest is +3. Otherwise, most of them have a +2. The copper has a +1 because it has 1 electron in the 4s. Scandium and zinc are not regarded as transition elements. Remember, what was our definition of transition elements? We said transition elements are those in which the ions have incomplete 3D. So if I have scandium and you write the electron configuration of scandium, it's 3D1 4s2. Now, when I remove these 3 electrons, the 3D is empty. So actually, it does not have incomplete d orbitals, so it is not regarded as a transition element. Zinc also, it has 3d10 4s2. So if it forms zinc 2 plus, for example, then I remove the 4s, but the 3d is still completely filled. So it is not regarded as a transition element. Okay, transition elements form complexes. So we need to talk about what's a complex and what's a ligand. Now, the ligand is a species that can donate a lone pair of electrons to form a dative bond to the central metal ion. So, for example, if I have chloride or ammonia or water or OH minus, each of these have lone pair of electrons. So the chloride ion has a lone pair of electrons. The ammonia has nitrogen with a lone pair of electrons. The water has oxygen with lone pair of electrons and also the OH minus. Now, these lone pair of electrons can be used to make a dative bond with a transition metal. And this forms what we call a complex. So the complex is the metal ion surrounded by the ligands. So the number of coordinate bonds or the number of bonds that the central atom makes is called the coordination number. For example, if I have this complex, now what do I have? I have chloride ions making a complex with the chromium ion. And this nitrogen, this is a ligand that has 2 nitrogens that each of them have electrons that can be donated. All of these bonds to the chromium are dative bonds or coordinate bonds in which the lone pair of electrons are used to make the bond. So this is what we call a complex. Now, the ligands and the complex ions are formed when ligands form coordinate bonds to vacant orbitals in the central atom. So we have copper with vacant orbitals, and this forms dative bonds with the ligands. All of this forms a complex ion. Now, what is the overall charge on the complex ion? The overall charge is the sum of the charges on the central ion and on each ligand. So, for example, this complex that we have with copper, ammonia and water have no charges on them. So ammonia is a neutral atom. We're just using the lone pair of electrons on the nitrogen to form a dative bond. Water is neutral. It doesn't have a charge. But the copper is a 2+ ion. So that means that the copper is 2+. Each of the ligands has a charge of 0. So the overall charge of my complex is 2+. What if I have this? Each of these ligands is a cyanide molecule. Now the cyanide has 1 negative. So each of these C triple bond N has 1 negative charge on it. And that means I have a total of 6 negative charges. Now the chromium in the middle has a +3 charge. So +3 minus 6, the overall is 3 minus. Again, if I have this, copper is +2. The copper ion in the middle is +2. Now, each of the chloride ions has 1 negative charge. So that means I have +2 minus 4, and that means the overall charge on that complex is -2. Okay? Then, how do we write formulas of a complex ion? What we do is we write the metal ion first, and then the ligands, and then the total charge outside the brackets. For example, if I have a complex between iron 2+ and 6 cyanide ions, then the complex will have an overall of -4, and the formula is FeCN, 6 bracket 4 minuses. Also, I have cobalt 3+, for example, with 6 ammonia. We said each of the ammonia does not have any charge, so the overall complex have a charge of 3+, and that's how we write it. If we start with iron 3+ and I have 6 cyanides, each of the cyanide has a negative, so +3 minus 6, I have an overall of 3 minus, and this is how we write the complex. Types of ligands. We said the ligand is the substance that makes a dative bond with the central atom. Now, if it makes 1 bond with the central atom, it is called monodentate. So a monodentate ligand is one that has 1 atom capable of binding to a central metal atom or ion. For example, we said water is monodentate. Ammonia, chloride, hydroxide, cyanide. So if I have cyanide, each of the cyanide can make 1 dative bond with the central atom. So we say it is monodentate. Water, if water is a ligand, we said the oxygen is the donor atom because the oxygen is the one that has the lone pair of electrons, and that makes the dative bond with the central atom. If we have ammonia, the ammonia is a monodentate ligand because the nitrogen will make 1 dative bond with the central atom. So these are monodentate. But if they can make 2 dative bonds with the atom, then we call them bidentate. So bidentate ligands have 2 atoms in their structure that are capable of binding to the central metal atom. These are bidentate ligands. So the oxalate has 2 O minuses that it can use to bond to the central metal atom. The ethylene diamine has 2 nitrogens. Each of them can make a dative bond, and so on. So these are called bidentate. So if I have bidentate ligands, each of them is making 2. So these are 3 of them, each of them making 2 dative bonds to the central metal atom. So we say that this is bidentate, but the complex has 6 dative bonds. Now, some ligands are polydentate. So they have more than 2 atoms that are capable of binding to the central metal atom. The main one that we talk about is EDTA. EDTA is this molecule on top it has 6 atoms that can make bonds to the central metal, so we say it is hexadentate. Okay, what is the structure of the complexes? Now, that depends. If we have something bonded to 2, then this is linear. So the silver ammonia complex here is a linear molecule. If we have the central atom bonded to 6 ligands, so it has 6 dative bonds, then its structure would be octahedral. We know that the octahedral means we have 4 on a plane, and then we have 1 on top and 1 below. So this is octahedral structure. Also, this has cobalt bonded to water and to Cl. They are a total of 6 dative bonds, so they form an octahedral structure. If the central atom is bonded to 4, but it has to be 4 large ligands. Chloride, for example, is regarded as a large ligand. So to have them, of course, these structures are to have minimum repulsion between the electrons. So this is a tetrahedral structure. So copper with chloride ions or cobalt with chloride ions forms a tetrahedral structure. Some are square planar, so this has 4 dative bonds, but they are on a square planar structure. So cis-platine and trans-platine, these are complexes between platinum and 2 chloride ions and 2 ammonia. Now, they can be arranged so that the chloride ions are next to each other, so that's the cis, or the chlorides are opposite to each other, so that is the trans. Now, the importance of this complex is that the cis-4 is used as an anti-cancer drug. It binds to the DNA in the cancer cells, prevents the replication of the DNA strands and cell division, so it acts as an anti-cancer drug. Remember that the cis-platine is square planar, platinum with 2 chlorides and 2 ammonia, and it is used as an anti-cancer drug. Now, some of these complexes have stereoisomers. Stereoisomers means they can be cis or trans, and we said cis like the cis-platine and the trans-platine. If the 2 of the ligands are next to each other, that is cis. If they are opposite to each other, that is trans. Also here, this also has a cis-trans isomer in which the 2 NH2s are on the same side of the copper or on opposite sides of the copper. So we say these are cis and trans. We can also have optical isomers. Remember that optical isomers are one in which we have mirror images that are not superimposable on each other. So this is an example of an optical isomer. This also is an example of an optical isomer in which the mirror images are not superimposable on each other. Most of these complexes of transition metals have very characteristic colors. Remember that we said one of the properties of transition metals is that they form colored compounds. That is because their complexes absorb in the visible spectrum, so they have different colors. Okay, why do they have different colors? You should know that the 5d orbitals are described as degenerate. Degenerate means all of them have the same energy. They're on the same energy level. So the 3D sublevel is divided into 5 orbitals, or has 5 different orbitals that are oriented in space differently on the X, Y, and Z axis, but they all have the same energy level. So we say they are degenerate. However, when the metal forms a complex, now these dative bonds repel the d orbitals. So we have dative bonds on the same plane with the d orbital or perpendicular to the d orbital. So this affects the energy levels of the 5d orbitals, which originally should have the same energy, but this repels them so that two of them have a slightly higher energy than the other three. So the 5d orbitals split. Two of them have a slightly higher energy than the other three. So when light shines on the solution, then the electron in the lower energy levels of the d orbitals will absorb a certain amount of energy equal to the difference, the delta E, between the two non-degenerate orbitals, and the electron jumps to the higher energy level. So electrons in the one of the lower three d orbitals will jump to the higher d orbitals, and the rest of the visible spectrum that is transmitted through the solution is the color observed. So some of the visible light is absorbed to allow the electron to jump to the higher energy level, and the rest of the colors is what we see. However, some of the elements do not have colored compounds. So if we're talking, for example, about the S block, why is it that transition metals have colored compounds while metals in group 1 and group 2 do not? This is because the ones in group 1 and group 2, the energy gap is too large to absorb visible light, so its compounds are not colored. So in the S block, no colored compounds because the energy gap is too large to absorb visible light. Also, some of the complexes that are formed have no color. So, for example, if we say the silver ammonia complex, in which silver is complex to two ammonias, this has no color. Why doesn't it have a color? Because this is Ag plus, and when we write the electron distribution of Ag, we end up with 5s1 4d10. Now, if I'm going to form Ag plus, that means I'm losing one electron. Of course, we said it will be lost from the 5s, and I'm left with a 4d that is completely filled. If the 4d are completely filled, then no transition of electrons happens between the d orbitals, and we don't see any. Okay, we can have substitution of ligands. That means ligands in a complex may be exchanged for other ligands. This happens if the new complex formed is more stable than the original complex, and the colors of the solutions formed depends on the identity of the transition metal ions. So different metal ions will give different colors with different complexes and different ligands. So the color changes in transition metal ions may happen as a result of changes in what? If I change the oxidation number of the ion, I get a different color, or if I change the ligand, or if I change the coordination number of the complex. So these will all affect the color of what we see. Okay, so let's take a look at this one by one. For copper 2 plus, you should realize that when we dissolve copper 2 plus in water, then we have a complex between the copper and 6 water molecules. This solution is blue. Please remember the colors. So copper 2 plus in water forms copper water 6, and overall charge is 2 plus. Remember we said each water has no charge and the copper is plus 2, so the overall is plus 2. Remember that this complex copper 2 plus solution is blue solution. Now, when we add ammonia, ammonia is ammonium hydroxide. Ammonia solution is ammonium hydroxide. Now, the copper 2 plus will form a pale blue precipitate of copper hydroxide. Then, if we continue to add excess ammonia, this copper hydroxide will exchange the OH with 6 ammonia or 4 ammonia and 2 water. In both cases, I end up with a blue solution. This is because this complex with 4 ammonia and 2 water or with 6 ammonia, both of them are copper 2 plus complexes that have a dark blue solution. Remember, we used to say the test for copper ions is what? If I add aqueous ammonia, it gives a blue precipitate. And then excess, we said the precipitate dissolves to form a dark blue solution. This is why it forms a dark blue solution, because it forms a copper ammonia complex and that has a dark blue solution. Please pay attention to the colors. If we add concentrated HCl to my copper solution, so I have copper solution, copper in water, which we said is a blue solution. Now, if I add HCl to it, then it exchanges the water for chloride ions as ligand, and this is a yellow solution or a yellow-green solution in which the copper chloride complex has copper with 4 chloride ions with an overall charge of 2 minus. We said this is because each of the chlorides has 1 minus. The copper is 2 plus, so overall we have an overall of 2 minus. So remember that if I have copper solution, which is blue, I add concentrated HCl, it will turn to yellow or yellow-green solution. Okay, so that was copper. Let's talk about nickel. Now, nickel in water forms a nickel-water complex, which is green in color. Remember the colors. We said copper was blue solution. Nickel is green solution. So I'm starting with a nickel-water complex, which is the solution of nickel in water, and that is green. Now, if I add ammonia solution, we're going to exchange some of the water for OH minus. This forms a gray-green precipitate. If we add excess ammonia, the precipitate dissolves and I end up with a blue solution in which the nickel is complex to 6 ammonia or 4 ammonia and 2 water with an overall 2 plus charge. This is a blue solution. What if we add concentrated HCl? Now, when we add HCl, then the nickel is now complex to 4 chloride ions with an overall charge of +2. This is a yellow solution. Please remember the colors. What about cobalt? Now, we've talked about copper, we've talked about nickel. Let's talk about cobalt. Cobalt 2 plus in water, in which the cobalt is complex to 6 water, is a pink solution. So we are starting with a pink solution in which the cobalt is complex to water with an overall charge of 2 plus. Now, what are we going to add? We are going to add sodium hydroxide. The blue precipitate is formed if you add sodium hydroxide to this complex. So the pink color forms a blue precipitate. This is cobalt complex to 4 water and 2 OH. The cobalt is +2, each of the OH is -1, so that means that my overall complex does not have a charge. So we have pink, cobalt solution in water is pink. You add a base, it forms a blue precipitate. Now, when we add ammonia, then we're exchanging the water with ammonia. This forms a yellowish brown solution. So the cobalt with 6 ammonia around it is a yellow brown solution. If you add concentrated HCl, I end up with a blue solution of cobalt chloride 2 minus. Are we following all of this? This is a complex in which the cobalt has 4 chloride ions, so it has an overall charge of 2 minus. For zinc, remember we said zinc will not have a color. So zinc in sodium hydroxide forms a white precipitate of zinc hydroxide. If you add excess, the precipitate dissolves. This means if I have the zinc with 4 OH attached to it, that is, and 2 minuses, this is a colorless solution. Vanadium, you should remember that vanadium in different oxidation states will have different colors. So +2, it is purple, +3, it's green, +4, it's blue, and +5, it is yellow. Some cations form green solutions. So these are the cations that form green solutions. Vanadium +3 with 6 watt. Iron +2 is green. Nickel +2 is green. Chromium with a +3 charge. Remember that chromium alone is +3. If it has 6 OH minuses, that means 6 negatives. With 3 positives, the overall is 3 minus. So this chromium is a +3 ion surrounded with 6 OH. All of these form green solutions. Chromium ions, we have chromium with ammonia complex, that is purple. If it is chromium in solution with water, it is blue. The chromium with the hydroxide ions around it, this is green. Now, you need to remember also that hydrogen peroxide is an oxidizing agent. So if it oxidizes the chromium to chromate ions, then it changes it from green to yellow. The chromate ions, if you add acid, it becomes dichromate, and the dichromate is orange. And if we want to go back, you can add base to the dichromate, it becomes yellow again. Are we following all of this? Okay, so these are the different colors for the chromium ion. Remember that we said ligand substitution of a monodentate ligand by a bidentate or a hexadentate, this leads to a more stable complex ion. And that means that the system will have a more positive delta S. So remember that removing a monodentate, replacing it by a bidentate or a hexadentate, this makes the delta S system more positive, and that means it forms a more stable complex. So if I have a monodentate ligand, then I replace it with a bidentate, or I replace it with a hexadentate, then these will be more and more stable complex ions. So remember that a hexadentate is more stable than a bidentate, and these are more stable than a monodentate ligand. You should remember that transition metals, one of their properties is that they act as catalysts. So transition metals act as catalysts. Transition metals and their compounds will either be heterogeneous catalysts or homogeneous catalysts. What is the difference between this? You should remember that a homogeneous catalyst is one that is in the same phase as the reactants. So if I have solutions and my catalyst is a solution, then these are homogeneous catalysts. But a heterogeneous catalyst is one that is in a different phase from the reactants. So if my reactants are solutions, but I put a solid as a catalyst, that is a heterogeneous catalyst. Homogeneous is one in the same phase as the reactants. Now, when it is in the same phase as a reactant, how does it work? It works through an intermediate species. So I'm starting with reactants and catalysts. The reactants have a certain amount of energy. Without a catalyst, then the activation energy is high. So that blue graph is the activation energy when there is no catalyst. But when there is a homogeneous catalyst, this forms an intermediate. The intermediate has lower activation energy, and this makes it easier for the products to be formed. So an example of homogeneous catalyst is when we have this reaction between thiosulfate and iodide to give sulfate ions plus iodine. This reaction is slow. We need a catalyst. We use iron 2 plus or iron 3 plus solutions. So all of these are solutions. Then it is a homogeneous catalyst. The catalyst is in the same phase as the reaction. Heterogeneous catalyst is in different phase from the reactants. So we said if we have solutions and we add the catalyst as a solid, that's a heterogeneous catalyst. Now, how does that work? This works because the reaction is adsorbed, or the reactants are adsorbed onto the surface of the catalyst. This makes it easier for the reaction to work. So, for example, we said if I want to do decomposition of H2O2 to give oxygen and water, we can use manganese dioxide as a catalyst, and that's a solid. Or hydrogenation of alkenes. We said when we add hydrogen to alkenes, the catalyst is nickel, and that is a solid. So these are examples of heterogeneous catalysts. So, for example, we said what happens is the nickel is a solid. It acts as a surface to which the reactants are adsorbed. This makes it easier for the reaction to happen, and then the products are released from the surface of the catalyst. An example of that is the catalytic converter in cars. So in the car exhaust engines, the catalytic converter has a catalyst which is platinum or palladium. The catalyst in the catalytic converter, what we're trying to do is we're trying to decrease the emission of dangerous gases. So in the engine, we have carbon monoxide, nitrogen monoxide, hydrocarbons released from the reactions in the engine. Now, releasing these gases into the atmosphere is dangerous. You should know that carbon monoxide is poisonous. Nitrogen monoxide causes acid rain. So we don't want to emit this into the atmosphere. This goes through a catalyst. These are gases, and they go through a catalyst. So the catalyst is platinum or palladium, and that is solid. So this is an example of heterogeneous catalysis. Now, what happens in the catalytic converter is that the presence of the catalyst causes these products to be formed. First of all, we said this is a heterogeneous catalyst. What happens is we have adsorption of the gases that we're trying to change. So carbon monoxide, nitrogen monoxide, these are adsorbed onto the surface of the catalyst, resulting in the weakening of the bonds so that chemical reaction can occur. And then the carbon dioxide and nitrogen molecules formed will be desorbed or removed from the surface of the catalyst. And this kind of reactions occur between carbon monoxide and nitrogen monoxide to form nitrogen gas and carbon dioxide gas. Remember that the products here are carbon dioxide, water, nitrogen. Of course, carbon dioxide is still a problem because this leads to climate change. So I cannot say that all the products from the catalytic converter are safe for emission into the environment. But of course, the effect of carbon dioxide is less than the effect of carbon monoxide. So this is what happens in the catalytic converter. But if he says all the products are safe to be emitted into the environment, no, it's not really safe because carbon dioxide can lead to climate change. Then there is something called autocatalysis. Autocatalysis is when one of the products formed in the reaction acts as a catalyst to speed up the reaction. So the reaction at the beginning is slow, but when one of the products is formed, it helps to speed up the reaction. So an example of this is the reaction between the ethane diowate ion with manganate ions. So the C2O4 2- reacting with manganate ions. This forms manganese 2+. Now, the initial reaction is very slow. Now, why is it very slow? Because both reactants are negatively charged, so the MnO4- and C2O4 2-, both reactants are negatively charged, so there is repulsion and the reaction has a very high activation energy. But once the reaction forms Mn2+, then this helps to catalyze the reaction and make it faster. So we call this autocatalysis. Now, hemoglobin is an example of an iron 2 complex. So in our blood, in the red blood cells, we have hemoglobin. Hemoglobin is iron 2 complex containing a polydentate ligand. The oxygen binds reversibly to the iron 2+ in the middle of this complex. So this is a polydentate ligand complex to iron 2+. When there is oxygen, then the oxygen binds to the iron 2+. So this is what we call oxyhemoglobin. But if there is carbon monoxide, then the carbon monoxide is the one that will bind to the iron 2+, and the dative bond formed between the carbon monoxide and iron 2+ is stronger than the dative bond between iron 2+ and oxygen. And that is why the oxygen, when it binds, it can be easily removed, but the carbon monoxide, when it binds to the hemoglobin to form carboxyhemoglobin, this is not easily replaced, and this causes poisonous. That is why we say that carbon monoxide is poisonous. So that is the end of this chapter. I hope this was useful to you. Please study all of this and please keep listening to the videos. Thank you.